Hi. Hi, everyone,
Hey, hello.
and welcome. I am Katie Fitzgerald, the Associate Director at the National Air Filtration Association. Thanks so much for joining us today. We are excited to kick off today's session, The Basics of ASHRAE 52.2 Filter Testing with Bobby Singer. Before I turn things over to our moderator, Matthew Brooks, just a few quick reminders about how NAFA is your go-to source for air filtration education and best practices. We're here to keep you informed, connected, and supported. Glad to have you with us.
Great. And before,
We've
oh,
go ahead.
no, go ahead.
Okay. Join us in Newport. We'll be in Rhode Island for our 44th annual convention in October. The convention's designed for business owners, executives, and managers in the air filtration, manufacturing, and distribution industry. We'll have cutting edge air filtration topics alongside business strategy sessions and invite your spouse or companion to enjoy the beauty of fall in Newport. Also want to remind you to save the dates for NAFA's technical seminar, which will be held in Louisville, Kentucky, April 2026. Join us for 2 days of dynamic technical sessions led by industry experts and thought leaders, where you'll gain a fresh perspective on latest research, emerging trends, and advanced practices in air filtration. Just to remind you that NAFA does go beyond the minimum standards that ASHRAE provides with our best practices and guidelines. These guidelines are free. You can download them off the NAFA website. It also allows you to brand them and add your company logo, leave behind as an educational tool for your clients. NAFA has 13 best practice guidelines that you can download, brand for free. It's a great way to show that your company is involved in the industry and follows the latest best practices of air filtration. They are all available free to download on the NAFA website. And don't forget to follow us on social media. Keep up with the latest in air filtration, education, industry news, and community discussions, wherever it's convenient for you, Facebook, YouTube, our podcast, LinkedIn. We also want to give a big thank you to our Platinum and Gold sponsors for their continued and valued support. If you're interested or would like more information in NAFA sponsor program, visit our website for additional details. I am going to now hand it over to our moderator, Matthew Brooks. Matt is the Education and Training Committee Chair. Thanks, Matt, for your contributions and moderating our webinar today.
Thank you so much. Appreciate it. Thanks for the introduction. And before I introduce our fantastic speaker today, I will be monitoring the Q&A section down at the bottom of your screen. You can see that's where you can submit your questions there. So please, any questions you have, submit there, and we'll try to get to as many as we can towards the end of the presentation. Now, our highly anticipated speaker today, Bobby, began his career in filtration testing in 1989 at Filter Testing Laboratories in Louisville, Kentucky, while studying computer science at the University of Louisville. He was there until 2005 when he joined Blue Heaven Technologies as lab manager. After a 10-year succession process, Bobby took ownership of Blue Haven in February of 2023. He is currently the chair of ASHRAE TC 2.4 Standard Subcommittee and is also a voting member of ASHRAE SSPC 52.2, which we'll be talking about, and TC 2.4 committees. On top of all that, we're lucky enough to have Bobby on the NAFA Board of Directors helping guide our organization with his expertise. So with all that said, Bobby, please take it away.
Well, thank you, Matt. I really appreciate that. And thank you, Katie, and all the NAFA staff for giving me the opportunity to talk here today. It's one of my favorite topics, ASHRAE 52.2. So welcome everyone that's good enough to show up to the presentation. Hopefully we can learn a few things. And let me try to take control here. Okay, again, this is me. I've been doing this for quite a long time. like Matt said, since 1989. So I've seen a lot of things and I've learned a lot of things. But anyway, let's get started. This is ASHRAE 52.2. This is a picture of the newest version of the method, which was just actually published a few months ago, ASHRAE 52.2 2025. This is more of a reprint than anything. It's just we've cleaned up some of the wording, make it a little more consistent, things of that nature. There's no real substantive changes in this version. The original version was published in 1999. It superseded ASHRAE 52.1, which was published in 1992. The original ASHRAE 52 was published in 1968, utilizing the old dust spot technology, which is what this method 52.2 replaced with the particle counting technology. The old dust spot was basically a filter paper installed upstream and downstream of a test filter, measure the opacity through each of those papers, and the difference in that opacity would be the efficiency. But of course, we've progressed technologically to where particle counting and things of that nature have made it necessary, of course, to update the method. But the method is overseen by ASHRAE SSPC 52.2. That is a standing standards project committee, which means the standard is maintained continuously. The committee meets twice a year to update, answer questions, make sure the standard is in good standing and all that kind of thing. The big deal with the method is that it introduced MERV, minimum efficiency reporting value, which I think we're all familiar with at this point. So what are we testing really with this method? The different steps of the actual process of the test. The first thing we would do is an initial pressure drop, which we're measuring the resistance to airflow of the filter. This ties in with energy consumption. The higher the pressure drop, the more energy it requires to push air through the filter. The lower the pressure drop, the less energy it requires. Clean efficiency. This is done on the new filter. So how well does the new filter remove particulate? Dust loaded or final efficiency. How well does the filter hold up through its life? As it gets dirty, how well does it continue to remove particulate? Average arrestance, that's how much dust the filter actually stops. And how well does it continue to do that throughout the life of the filter as the pressure drop goes up? The final pressure drop, or the change out pressure drop, some might call it. How strong is the filter? How well does it hold up to that final pressure drop? How well does it remove particulate up to that final pressure drop? And then dust holding capacity. I'd like to say it equates to the life of the filter, but the truth is it does not. The dust it's going to see in its application is going to be much different than ASHRAE test dust. You had to have some synthetic test dust to be able to use in a laboratory environment to compare filters. ASHRAE dust is what they settled on. So while it doesn't equate to filter life, it can be used to compare filter to filter. This is a mock-up of a typical ASHRAE 52.2 duct. You can see the far left side is where the air would enter. That's the upstream side. This tall housing would contain the blower, the fan that pushes the air through the duct. Under that would be HEPA filter. So we're cleaning the air before it's introduced into the test rig. Let's start my little cartoon here. Again, the upstream side, the air is going to push through this way. I'm going to try to pause it here. Right there. So the air is coming through this way. This is the particle generator. So there's a distilled water potassium chloride solution here, which is pumped into this tower where it's aerosolized. The particulate is dried, where it's then introduced into the test rig. So the air pushes it down through the rig, We got a particle counter here. So we're sampling the air before it goes through the filter. The filter would be mounted in this test section here. And then we would have a particle counter downstream where we're sampling the air once it's been cleaned by the filter. Downstream of that is a flow orifice, which is how we measure the flow. So you can see, I don't know how well you can see it or not, but there's a static tap would be upstream and downstream of the filter here. Those would go to a manometer. That's how we measure the resistance to airflow or the pressure drop of the filter. And the same is done across the orifice. That's how we know how much flow we're pushing through the test duct. So we'll continue our illustration here. This is the dust feeder. So the ASHRAE dust will be placed into that feeder when it comes time to load dust, introduced down into the duct, into the filter. Pressure drop goes up. This is the upstream most end. So you see the louvers where the air would be allowed to come into the blower to push through. This is our control station. That's just how we would control airflow, the particle counters, things of that nature. The downstream end, you'll get kind of a backside view of the flow orifice here in a second. And we'll get an up close look at that here in a minute, but right there would be the flow orifice. And then the most downstream section has HEPA filters in it. So we're cleaning the air before we dump it back into the space. So that is a typical ASHRAE 52.2 test rig. I mentioned the flow orifice. This is a good illustration of what that looks like. Typical ASHRAE ASME flow orifice. This is a pretty small one. This would probably be used in one of our flat sheet testing rigs where we would test at a low flow. Typically in an ASHRAE duct, we'll use more like a 9 or a 10-inch orifice plate. But again, we're measuring the pressure drop across that plate. The pressure drop, depending on the size of that hole, is how we know how much flow we're pushing through the duct. So the larger the hole, obviously, the more air going through. So we would use a larger orifice at the higher flows, smaller orifices at the lower flows. So again, I mentioned the static taps upstream and downstream. Those would be upstream and downstream of the filter. That's how we measure pressure drop of the filter, and then the same for the orifice for measuring the flow. For an ASHRAE standard test, we would measure the pressure drop across the filter at 50%, 75%, 100%, and 125% of rated flow. So you get a nice curve of pressure drop readings. We talk about pressure drop, and then we talk about MERV, the particle removal portion. So how is it sliced and diced? We're measuring from 0.3 to 10 microns in 12 different size ranges. You can see those ranges here. The smallest 4 channels from 0.3 to 1 micron. The efficiency at those sizes would be averaged. That's E1. The E1 efficiency would be the average efficiency from 0.3 to 1 micron. The middle 4 sizes, the 1 to 3 micron, the efficiency at those sizes would be averaged. That's E2 efficiency. The larger 4 sizes, from 3 to 10, the efficiencies would be averaged. That's E3. So E1, E2, E3, plug them into the MERV table. That's how we get our MERV rating. Move along. So this is the MERV table. I'd like to hope most people are familiar with this, but you see the ratings here from 1 through 16. Your E1 range that we mentioned from 0.3 to 1, E2 from 1 to 3, E3 from 3 to 10. So if you look here, your range 1, these are really insignificant until you get to MERV 11, where there's a 20% requirement in E1 to make MERV 11. You see the E2 range, really insignificant until you get to MERV 8, again, a 20% requirement. E3 range doesn't become a factor until you get to MERV 5, where there's a 20% requirement. So what happens if you're less than 20%? In those cases, the MERV is established by the arrestance percentage of the filter, the average arrestance. That's the percentage of dust that the filter stops through the test. So you can see there's a 75% requirement for MERV 4. So if we were to load 100 grams of dust, the filter stops 75 grams, 75% MERV 4. That's how that works. So if you see something less than a MERV 5, you know that the MERV was established via the arrestance percentage of that filter. So we talk about all these particle sizes, and I think it's important to put them into perspective. You know, we're measuring from 0.3 to 10 microns for this test. So you take an average grain of sand, and it's somewhere in the neighborhood of 90 microns across. A human hair, somewhere in the neighborhood of 50 to 70 microns across. Combustion particles, metals, organic compounds, things of that nature, smaller than 2.5. And then dust, pollens, molds are PM10, so they're 10 micron and smaller. So this gives you a good indication of how small we're really sampling with this equipment, down to 0.3 micron. It's pretty impressive if you actually think about it. So ASHRAE dust, when we dust load the filter, this is some nasty stuff, to be quite honest. This black powder here, this is what it looks like. The composition is 72% isofine, 23% powdered carbon, 5% ground cotton, blended together to form this nice black powder. The process of the test, we would run the initial efficiency, as I mentioned before, on the clean filter. Then we're going to load dust. We're loading dust basically to mimic the life of the filter. So our initial load is going to be 30 grams of dust or a rise of 0.04 inches in water column. Then we run an efficiency measurement, a particle removal efficiency measurement. The load 2, our second loading, we're going to load to 25% of the difference between the initial pressure drop and the final pressure drop. Then we would run another particle removal efficiency. Then we would load to 50% of the difference between the initial pressure and the final pressure, efficiency measurement, then load to 75, and then to the final pressure drop, run our final efficiency measurement. So you're getting particle removal efficiency measurements throughout the life of that filter. And we talk about pressure drop, and again, I like to put things into perspective. So what does an inch of water column really mean? Well, an inch of water column is equivalent to 0.036 pounds per square inch. So if you take a 24-inch by 24-inch panel filter, that contains 576 square inches. So 1 inch of water column, if you do the math, is equivalent to about 20 pounds of weight distributed evenly across the face of that filter. What happens to weigh around 20 pounds? A case of beer. So you can kind of visualize the kind of weight that we're talking about. It's actually quite a bit of pressure if you really think about it. All right, so once we've completed the process, we issue a test report. And this is generally what a test report is going to look like. Your page 1 or your cover page, be a filter description here, the filter manufacturer, model name, part number, size, things like that. We started including pictures of the filters quite a few years ago. Then you get your test results here towards the bottom. Test conditions obviously above. Shows the type of test dust, which should always be ASHRAE dust, the barometric pressure, temperature, humidity. This is the meat of the cover page. Shows your E1, E2, E3, which we talked about, what ranges those are. The flow rate, which is really critical. ASHRAE allows for several different flow rates to be used. It's important. The MERV rating is at a specific flow rate. So you can take this MERV 13 filter, maybe test it at half the flow, and maybe it's a MERV 14. It's important to know what flow the test was performed at. We're going to list the clean resistance of the filter, the final resistance of the filter. Again, important to know dust holding capacity to 1 inch is not going to be the same as it is to 1.5 inches on the same filter. So it's important to know these little details when you're looking at a report. And then obviously the MERV rating. Okay, this would be our graph page, which shows, I mentioned the pressure drop curve of that clean filter. That's what this would look like. And then the efficiency measurements at those different dust loading points graphed. And then in table form, you can see the size ranges, those 12 ranges that we mentioned. And then your initial efficiency. So this was the removal efficiency of the filter clean. Our load 1, you can see in this case, it took 7 grams to get it to go up 0.04 inches water column. So that's our efficiency data at that point. At our load 2 point of dust loading, load 3, load 4, and then at the final pressure drop. So you can see how well the filter is removing particulate as it gets dirty. The important thing I want to point out here is this highlighted in yellow column here, CME, cumulative minimum efficiency. By definition, we're wanting to report the minimum efficiency reporting value. So what happens through all these efficiency measurements, we're going to pull the minimum that we get in each size, no matter where it is, over to this cumulative minimum efficiency. So that minimum efficiency is going to come over into this column here. These are the numbers that determine the MERV rating. We're averaging these 4 for E1, these 4 for E2, and these 4 for E3. So it truly is the minimum efficiency from this test. All right. Another thing I want to point out is making the connection. Based on your application, you can look at this in different ways. We mentioned E1, E2, E3. So there's our E1, 0.3 to 1, 1 to 3, and then 3 to 10. So if I'm in an application where I'm selling to a hospital or I'm buying for a hospital, I might want to pay a lot of attention to E1. Those are those small particles that actually make people sick. So that's important to pay attention to. The E2, that would be more in the HVAC world. You talk about MERV 8s through 13s, E2s, as I mentioned, that's where that becomes relevant. The larger particles, that's more of your industrial applications, your paints and things of that nature. So it's important to know where the filter is going to go and to look at the data that's presented to make more educated decisions. The process of operating and maintaining a 52.2 test duct is not easy. We get questions a lot of times, can you build us a test rig? And it's like, we could, but we're not going to because you don't want that. It's a lot of trouble, maintenance. There's a qualification procedure that has to be adhered to. We have to prove that we have velocity uniformity through this test duct. We can't just throw it together, throw some counters on there and start testing. We have to show that the velocity is the same in the middle of the duct as it is in the upper left-hand corner of the duct and the lower corner of the duct. The same with the aerosol. When we generate aerosol, we have to prove that we're getting basically the same concentration in the top corner as we are the bottom corner. It has to be evenly distributed. We have to show that the duct doesn't leak. We pressurize the duct to make sure it's not leaking. Downstream mixing, we have to prove that no matter where the penetration is happening on the filter, that we can sample it with our probe or sampling port that's mounted in the middle of the duct. Particle counter sizing accuracy, we have to show by feeding a particle of a known size to our counters that when it counts at 5 micron, that it really is 5 micron. These things have to be proven. And that's just to name a few of the steps that we have to go through. If you really know what you're doing and you don't have any problems, this process can take about a week. If you do have problems, you can be looking at 2 weeks, maybe even more. So there's more to it than meets the eye. We do have to talk about Appendix J. It's kind of become a big deal in the last few years. Many filters will utilize electrostatic charge to enhance particle removal efficiency, and it's able to do that while maintaining a low pressure drop. That's the beauty of the electrostatic charge. If there's an issue with it, it's that charge will dissipate over time to some degree. The Appendix J is an optional method. It's designed to mask that electrostatic charge so we can see how well the filter is going to remove particulate when that charge is taken away. We dissipate that charge or mask that charge by mass loading of fine potassium chloride particles. So what we would do is run an efficiency measurement. Then we would expose the filter to these fine potassium chloride particles and then run another efficiency measurement. If the efficiency drops 2% or more in 2 consecutive size ranges, then we repeat that process. We keep repeating it until the efficiency does not drop. So the test can be quite time consuming if you're testing a filter that is charged. If you have to repeat that process, which obviously means it can get expensive. The data product of that Appendix J is MERV A. So what else is out there? What's comparable? EN 779 is I think of it as the European answer to ASHRAE 52.2. It has similarities, it has differences. It uses DEHS, which is an oil, as aerosol challenge, as opposed to the KCl or potassium chloride. It measures from 0.3 to 5 micron as opposed to 0.3 to 10. It does utilize the same test dust ASHRAE does, so you could compare dust holding capacity between the two standards. The data product is based on average efficiency as opposed to minimum efficiency. So the loading process is similar, and you run those efficiency measurements throughout the loading process, but those measurements are averaged specifically at 0.4 for the rating. This method technically was superseded by ISO 16890 in 2016, but we still run a ton of these. Apparently, this method is written into a lot of specs throughout the industry, so there is still demand for this test. If you see a filter rated as G, M, or F, you know that it was tested to EN 779 standard. The other one, which is a bigger deal, I think, is the ISO 16890. It still feels like a new standard, even though it was published in 2016. It was intended to be a global test method, and it basically has become that, minus the United States. The U.S. is holding on to 52.2 for dear life, apparently, and it doesn't seem like it's going to change anytime soon. But if you're doing business globally, this method is going to rear its head eventually. It has a lot of similarities to 52.2. The measurements are in the same size ranges, 0.3 to 10 micron. It does, however, use the oil, the DEHS, for measuring from 0.3 to 1 micron. It uses potassium chloride or KCl in the 1 to 10 range. So that is directly comparable to 52.2. The discharge procedure is much different. As opposed to the Appendix J loading of particulate, it utilizes a 24-hour discharge period in a IPA vapor chamber. So we have IPA alcohol in trays in this chamber, place the filter in for 24 hours, the vapor dissipates any electrostatic charge. So you test it before and after that discharge process. Those two efficiencies are averaged. And that's where the data product comes from. It's listed as EPM1, EPM 2.5, or EPM 10. The dust used in this method is ISO fine dust, which is important to take note of because ISO fine dust will usually show anywhere from 3, maybe even 5 times the dust holding capacity that ASHRAE dust will show. It's important to know what type of dust was used when you talk about dust holding capacity. Things to look out for, we've already mentioned ISO 16890. It's intended to be the global test standard. And again, the world is pretty much adopting it, especially Europe, but the US not quite so much so far. ASHRAE 241 caused a big splash in the last few years. That's a building code. It's optional. It's not a mandatory thing by any stretch. But if a building manager or owner decides to adopt this code, filters that go into that installation have to be MERV A rated, which means they have to have been tested to Appendix J, which can be a big deal again when you talk about testing budgets and things. The latest version of the standard, I said there weren't a lot of changes, but there was Appendix L introduced. This is an optional test for removal of bioaerosols. This type of testing has become a big deal since COVID. There's also an ASHRAE 185 that is a multi-pass chamber test for particulates and bioaerosols. The idea is a more realistic test. It's, as I mentioned, it's a multi-pass. So you're testing within a space as opposed to just before and after a single pass through a filter. One important thing that a lot of people don't know about that I wanted to mention is a few years ago, ASHRAE 52.2 Addendum B was released. This allows for reporting of PM1, PM2.5, and PM10. They call it PM52.2. So with the data that's already produced within the test, we can calculate these numbers. In closing, I have some information packets, the MERV table, some comparison charts, things like that. I invite you to write my email address down. If you would like any of that information, feel free to email me. I would ask that maybe in the subject, in the header, you put NAFA webinar or something to that effect so I know what I'm looking for. But you are welcome to email me if you're interested in any of that information. And with that, I'm happy to take questions. Thank you.
Awesome job, Bobby. Thank you so much for that. You are a wealth of knowledge. We do have a lot of questions that came in with people registering. We have questions coming in the Q&A. If you do have questions, put them down at the bottom of the screen there in that Q&A section, and we'll try to get to as many as we can. One question that came through that I thought was kind of interesting, Bobby, to kind of kick us off here is when you're explaining ASHRAE 52.2 to a person who doesn't understand, how can you do that simply?
How can you do that simply? Well, we're quantifying how well a filter removes particulate of certain sizes, and how well it stops dust. To put it quite simply, I don't know that it's possible to explain it in a very, very simple way, unfortunately. Without a good description of MERV, it's hard to understand exactly what it is. But
I agree. That's why I thought it was an interesting question. But I do like how you kind of answered that. It's you're talking about how you get that efficiency rating and how you in the purpose of stopping dust, and that's a lot of applications. That's really what the filter's there to do. Staying on that dust topic, I got a couple pokes on. You mentioned the filter. I'm trying to put a couple of these questions together. You mentioned the dust holding capacity performance isn't the same as its real life capacity. Can you explain that a little bit more?
Well, the dust contaminant that a filter is going to be exposed to in Minnesota or Minneapolis is going to be much different than what it's going to be in New York or Los Angeles. And it's almost definitely not going to look anything like ASHRAE does. So, finer particulates are going to load differently than, if you're next to a cotton mill, or, if you're next to a cotton mill, that filter is going to load differently than it will if you're next to a concrete plant. So that's why you can't really equate ASHRAE dust holding to actual filter life. The variables are too great.
Great, but in the lab situation that you guys have at Blue Heaven, they can be compared to an extent. And that's what I think that was your caveat to that, is saying, hey, in this controlled scenario, that's how you can compare it. Is that accurate?
That is accurate. And it's important to know, though, that this is a laboratory environment. You know, they had to use something to simulate the dirtying of a filter. And this is what they arrived on however many years ago. And yes, you know, you can, it's kind of a good, better, best in terms of dust holding capacity. You can make assumptions, but you can't make direct correlations to filter life based on the dust holding with ASHRAE dust.
Great. He's actually kind of lining up nicely. So thank you, all the participants. You guys are firing off a lot of questions. There were a couple questions on how the filter fits in the frame. And I'm going to guess in your lab, there's some science behind that might not be in your everyday air handler. So how important is the seal of that filter?
It's fairly important. We don't rely on gasketing or anything of that nature. We actually seal the filter in with tape. Every time we test the filter, it's sealed in with tape. So we know that it's sealed in. You know, relying on gaskets can get tricky. You know, inevitably part of it's going to erode or something of that nature. So we take care to seal every filter in every time with tape, which again, when it's installed, you know, in its application, it's not probably going to be sealed in as well as we're sealing it in, but in a laboratory environment, it's important to do that. But, I don't know that it's scientific or not, but yes, we take care to seal them in with actual tape.
Well, what would the impact be if you didn't seal it in with tape and there was some bypass there?
Well, you're going to get lower pressure drop falsely, and you're going to get a bit of a lower efficiency. You know, it depends on, you know, the size of the gap and things like that. I think it was Dr. Jeff Siegel did a research project on this. But anyway, it's not, obviously it's not going to test as well. Now it will show lower pressure drop, which, you know, could be a false positive, I guess you would say, if you're not sealing it in properly, because you're getting the air that's going, you know, path of least resistance around the filter as opposed to through the filter. And for those exact reasons, your efficiency could be slightly lower because your air is not being filtered as it should due to the bypass.
Awesome. Okay. And in regards to pressure drop, there are a couple people asking about pressure drop in your system compared to a real world system. I don't know if that's really a question we could put in there, but the test duct you have has a designated, or at least a controlled volume and velocity of air, and that's adjustable. Or in that testing, is there always a standard amount of air at a standard speed that you're using for the 52.2?
No, it's adjustable. So I think I mentioned in the presentation that there are 7 allowable flows according to the standard. Now, those don't cover every application. So sometimes we would test outside of those flows, you know, if someone has a special circumstance. But we adjust the flow, you know, for example, industrial filters or commercial filters would be tested more in the range of 500 feet per minute, whereas residential filters would be tested more in the range of 300 feet per minute. So we can adjust the flow through our rig to accommodate whatever flow makes sense. And again, you know, we'll test filters that are smaller. You know, a 20 by 20 is going to be tested at a lower flow than a 24 by 24 filter would be. So we do adjust the flow depending on the situation.
And is that determined by the manufacturer or the person requesting the test?
Generally, yes. Obviously, we try to guide our customers. You know, sometimes we're asked to test at a flow that doesn't really make sense. You know, if somebody asks us to test a V bank at 300 feet a minute, we might say, yeah, you know, 500 feet a minute will probably make more sense. But yes, I mean, we're bound by what our customers ask us to do, of course, but we give guidance as best we can.
And they would also be determining, hey, we want to see what the dust loading and the pressure drop is at 1 inch. Like you mentioned, you can also run it to 1.5 inches or whatever number they might want.
That's correct. According to the standard, the only requirement is that you test to at least twice the initial pressure drop. So if your initial pressure drop is 0.2, your final could be 0.4, and you're within the bounds of the standard. Now, nobody does that, but that's the only requirement. So we could, yeah, if the customer requests to test a 1 inch or 1.2, 1.5, 1.8, that's what we'll do.
Great. Okay. And this is a little bit off topic. I actually don't know the answer to this one. I answered a couple of them live. Does ASHRAE 52.2 have any account or designation for a natural or a fiber, what the filter fiber is made out of?
Not that I'm aware of, no.
I didn't think so either. So I'm going to jump back into Appendix J because there's a ton of questions there. So when you're looking at this, and I'm going to try to filter through a bunch of these. You're welcome to everyone for that one. When you're looking at the Appendix J, does everyone always run that, or is that an optional thing?
It's optional. I'm not going to say it's rare that we run it. It's become more in demand over the last few years, but it is optional. We test far more to just the standard 52.2 than we do Appendix J.
So two people asked different varieties of this question, but they're asking if the Appendix J is the reason that some filters are now jumping from what have always been a MERV 14 to a MERV 15, or what was previously a MERV 8, and now they're testing out at a MERV 10. Is that part of Appendix J, or is there something else going on there?
I would say that's probably not part of Appendix J. It could be in a roundabout way. If you're talking about a filter that's going to lose efficiency through the discharge process, then maybe it's a MERV 10 and then it's a MERV 8A, if that makes sense. So it's, a lot of filters are labeled MERV 11, MERV 8A. So through the discharge process, it's going to fall to an 8. So you might see higher efficiency filters so that it has room to fall back to, say, a MERV 8A or something of that nature. That's the only reason I could think that could be the case. But generally speaking, I don't really think that that's directly related to Appendix J.
And Appendix J doesn't have any connection to ISO 16890, does it?
It does not, no.
So why, a couple people, when you mentioned it, why isn't the U.S. adopting 16890? Is there something that's different or unique about it that maybe some people haven't accepted on it yet?
There are a few things. It's kind of complicated to go into here, but there is depending on the efficiency of the filter, there's a rural aerosol distribution and an urban aerosol distribution that have an impact on the efficiency numbers. It's not really a huge impact, but it has an impact. And there's a lot of discussion going on. A lot of people don't like that, to be quite honest. That's probably a small portion of the reason why it hasn't taken. I think more than anything, it's 52.2 is what's always been done in the U.S. and change is hard. There is some discussion about the discharge process. There's a portion of people out there that don't like the discharge process. The IPA vapor can have some negative impact on some fibers and things like that. There is no perfect method. There's people that like this one and don't like that one, but I think resistance to change might be a lot of it. They're both, obviously valid methods. It's one thing when you've got, 30 years of data from 52.2 that's not all that comparable to ISO 16890, that's going to be a tough pill to swallow. I think that has a lot to do with it as well.
Sure, that makes a lot of sense. And those conditioning steps and being in different areas, that might have a lot to do with it too.
I love you. Have your dinner, okay?
Love Emily's joining us a little bit on that. That's all right. So I have a very specific question that you might have a quick little punch answer on it. So is it mandatory to have all 12 particle sizes to fill out that E1, E2, E3? Is that a mandatory part of the step, or is that you guys going above and beyond?
So it's mandatory. Yes, it's part of the standard.
So anybody doing that test has to do that.
Yes, you have to measure in all 12 sizes. Yes, if you're going to have a valid 52.2 test. Yeah.
So then there's some other questions saying that there's either mobile or in-house testing being done, and they're wondering how that might compare to an official test. And I guess there's just, it depends, right? I would imagine there's not really a clear-cut answer to that, but what would you say to people asking you about people that have mobile units or in-house testing?
You're right in your assumption of the answer. There's a lot of variables. Some people are going to do it better than others. Now I've seen test rigs. It's basically like a 52.2 test rig, but they're using ambient air as their challenge. And in that case, you're not going to see many of those larger particles, the 3 to 10 micron particles. So your E3 numbers are probably not going to be real comparable to a 52.2 test run as it should be. The in situ testing, you're not going to have, like I mentioned, the velocity uniformity, the aerosol uniformity, all of those things are going to be variables that have to be taken into consideration. The way I look at those is those are more of kind of ballpark numbers. They're not useless by any stretch. You can get some ideas in doing that, but testing in a laboratory is just a completely different animal than testing out at a site. There's a lot of variables that can go into it.
Great. Okay. And I have two questions on your 52.225 PM testing. You mentioned that towards the end that there's a kind of a updated PM
52.2, yes.
Thank you. Can you explain that a little bit better for us, or a little bit more?
Yeah, it was kind of 52.2's answer to 16.890 in some ways. PM PM reporting is a big deal. It's listed in a lot of standards, so they wanted to address that, and the data is there really. When you look at the ranges, you're measuring from 0.3 to 10 micron. So basically everything from 1 micron and smaller, those are your PM 1 52.2 efficiencies. It is a little skewed in one way. You're basically from 3 micron and smaller is going to be your PM 2.5, and then your 10 micron and smaller, all of those average is going to be your PM 10 52.2. So you're taking that data that you already have, and you're just running some simple math to establish what those PM 52.2 numbers will be.
So they're going along with this ASHRAE recommendation. There's some questions about with your involvement with ASHRAE. Do you see 52.2 or MERV changing in the next 5 years?
No, I do not. Yeah. To put it simply, there's been some major votes have happened over the past 5 years. There was a motion to make Appendix J mandatory. It was voted down. There was talk of possibly changing or shortening the process to include Appendix J. None of these have really taken root. So as far as I can see, nothing's going to change anytime really soon. So in the next 5 years, I don't really see any major changes happening, to be honest with you.
And you just said the Appendix J making it mandatory was voted down. Was there Was there reasoning behind that?
Well, I'm sure there was. I I wasn't privy to everyone's reasoning. There's a lot of concerns with it. Basically, we didn't want it to be mandatory. It would change a lot in terms of the cost of the test, the length of the test, things of that nature. Again, I'm there's a lot of different representatives in that room that have a lot of different reasons, and to be honest, I'm not privy with all of those reasons.
Someone gave us a pretty good one. So in regards to the test duct itself, is the air being drawn ambient HEPA filtered air? And can that be supplied through a chamber similar to ASHRAE 185.5 or ASHRAE 234? And is that air single pass? So that's kind of a loaded question. So first, is that air HEPA filtered ambient air going into the test rig?
No, not really. It's controlled. We have to control the environment. There are restrictions on humidity. That's the big one that you have to control. So to use ambient air, the humidity would be a problem. The range that they give you in temperature is wide enough that it probably wouldn't be a big problem in that regard. But you have to be between 35 and 55% humidity for the 52.2 test. So in the winter, it's lower than that. In the summer, it gets higher than that. So that's what would prohibit you from using ambient air. So we're using room air that is conditioned to meet those temperature and humidity requirements. Then it's being cleaned through HEPAs and introduced into the duct.
Okay, and then it's exhausted, or is it recirculated?
It can be either. Ours is exhausted into the room. So you'll have some U-shaped ducts where it's actually recirculating, but ours is not that way. Our rig is just in the illustration. It literally looks exactly like that. So it's just a straight line. Part of your other question was, is it multi-pass, or it's single pass? So it's just you're measuring one pass through the filter.
Awesome. There's two questions on energy consumption. Do you have any calculation, or do you guys track energy consumption? I don't know if you really would have anything to do with that in 52.2, but now I'm curious. Do you guys do anything on the energy side when it comes to air filtration?
We don't really. There's an energy consumption calculator in, I think, the EN 779 method, which is actually no more technically. There is no energy consumption calculation in 52.2. There are a lot of manufacturers will have their own calculator. It's difficult because you don't, the dusts are different. You're talking about well, it's not different in the laboratory, of course, but to use that in application, so many variables exist, the fan curve, things of that nature that make it difficult to calculate. But the answer is no, we do not calculate that here in our lab.
There was a couple questions comparing 52.2 testing to a HEPA test, and somebody asked if you could do a HEPA in a 52.2 test rig. Can you just without diving, I know that's a whole nother topic. Can you kind of brush the top of that just so people can understand that there's a lot of differences there that you know way better than I do?
Yeah, you could test a HEPA filter in a 52.2 rig. I mean, odds are you're going to get a MERV 16 every single time. The problem is that you can be MERV 16 and have 100% basically across the board in every range within the 52.2 test. That doesn't necessarily mean that you're going to be 99.97% efficient at 0.3. We're measuring from 0.3 to 4, so we're not technically measuring at 0.3. So while you can be MERV 16 and 52.2, that doesn't necessarily mean you're going to have a HEPA rating. to do that, a true HEPA test, there's several methods, EN 1822, ISO 29463, where we're measuring much smaller particle sizes. The equipment is much more sophisticated for those tests. We do perform those tests, but you could be a MERV 16 and not be a HEPA. But if you're a HEPA, you're definitely going to be a MERV 16, if that makes sense.
That does make sense to me. A couple questions on it. For those of you that aren't familiar with NAFA, we have a certified air filtration specialist test, and somebody I think jokingly asked, "Is this going to be on the test?" And I appreciate that, and the answer is who knows. But read the book.
Yeah. Maybe we have some material here that we could put on the test next time.
That's right. While you were asking that, someone asked about ALPA testing. Can you test down to ALPA efficiency with that 52.2? And I think your answer kind of covers that as well, but correct me if I'm wrong.
No, you're correct. To test, you need to identify most penetrating particle size for those tests, and you're not going to be able to do that in the ranges we're measuring in ASHRAE 52.2.
Got it. Now we have a lot of other questions that I'm sorry I'm not gonna be able to get to all of them. But what I think we're gonna do with Katie's help, we're either gonna put together an article that we can have a FAQ or at least some questions that were asked that we didn't answer, or maybe even recapping some of the ones that we did, sent out to everybody that was registered on this. There will be a recording. A couple of people asked. I did answer a couple of you. I know there's a couple more that I didn't get to. But Bobby, I appreciate all your time and effort that you put into this. And if you wouldn't mind one more time letting people know who you are, where you're from, and that you have your information there that you're willing to share with everybody.
Again, my name is Bobby Singer. I'm with Blue Heaven Technologies. We're in Louisville, Kentucky. My email address, I hope you can still see it on the screen, bobby@blueheaventech.com. I'm happy to share some information. We have, the MERV table and a comparison chart between the standards that can be useful to you. I'm happy to share those if you want to send me an email. I'm happy to answer questions. I know we probably have a lot that we're not able to get to. I apologize for that. But again, we'll try to address those if possible, and we'll try to put something together in the future to help answer any questions. I appreciate it.
All right. Well, thank you so much for joining us, everybody. Again, Katie will be getting the information out there, and hopefully we'll get that out soon. So thank you so much for joining us. Katie, did you have anything else that you wanted to touch base NAFA wise? I know we have our upcoming convention coming up that you did mention, and
Yeah.
I'm not sure if there's anything else on that.
Sure. Register. We also have another webinar coming up next month. So register online for that. It's with Tim Mohan on data centers and air filtration.
Great. We'll see everyone there. Thanks again, Bobby. Take care.
Thank you very much. I appreciate it, Matt. Katie, thank you.